Okay. Okay, this is an overview of Chapter 10, looking at our central theme of gas. How does it behave? How do we deal with pressure, volume, temperature, things like that? But in order to get there, we got to look at, okay, from gas, we got to talk about particles. Well, we refer to gas in terms of the gas particles. We don't talk about molecules and atoms, but basically, that's what they refer to as, that is what they refer to the particles as. Okay, instead of calling it gas molecules and gas atoms, we say particles. That makes it a lot easier. Now, of course, the thing about gas is that there's also something called pressure. Okay, and that's a pretty important thing when you're looking at gases because, well, the question comes down to is, what is pressure? Well, if you stop and think about it, the idea behind pressure, it's a force over an area. That's what we mean by gas, okay? Looking at gas, putting pressure on a wall, on a container, on us, okay? And that's force over area. But how? How is the next question? How is pressure actually created? And of course, we're looking at two connections here from pressure and force over area. Okay, how does that happen? Well, if you think about it, particles inside a container, whoops, misspelled it, particles, excuse me. So particles are hitting the container sides. That, ladies and gentlemen, is what's going on. The particles hit the container sides, and that's how we end up getting pressure because of force over area. Now, okay, let's bring down the pressure again. Okay, so with that, we know this is what happens with pressure. So I'm going to bring in the pressure again. Now, in the pressure, there is also temperature. There's also volume. How do they affect the pressure? Well, if you think about it, for temperature, normally, if you increase the temperature, you increase the pressure. Decrease the temperature, you decrease the pressure. But why? Okay, that would be an important question. Why would that matter, basically? Okay, well, the idea behind that has to do with temperature. Temperature is heat energy, okay? If we look at that, I'm going to use red for this. Temperature increases kinetic energy of the particles. Now, if the temperature is increasing the kinetic energy of the particles, then that means the particles are going to be moving around faster and they're going to be hitting the container on the sides as well at a faster speed. And what happens as a result, ladies and gentlemen, is that you're going to have a higher pressure. Now, volume. What's going on with volume? Well, volume has got to cross over here. And the basic idea is, if you increase the volume, you have a decrease in pressure. Decrease the volume, you have an increase in pressure. Think about a balloon, okay? If you blow into the balloon, all right, if you blow a little bit into the balloon, you have a small volume, okay? So there's going to be more pressure. If you keep blowing into it, you increase the volume, but at the same time, you've got more pressure in there. But what if you could expand the volume even more? Well, if you expand the volume even more, then the overall pressure goes down. Why? Because there's more space for particles to run around and hit. Okay? But if the volume gets smaller and you haven't changed anything, not the number of particles, not the temperature, then the pressure is going to go up, way up. That's the basic idea. So now that takes us to our gas laws. With the gas laws, there's a few things we have to look at. We've got to look at pressure, temperature, and volume. Those are the three basic things to look at. And we can talk about Boyle's law, okay? So there's Boyle. And Boyle basically said, look, keep the temperature the same, then P1 V1 is equal to P2 V2. All right? I'm going to erase the little dot here. So pressure 1 times volume 1 is equal to pressure 2 times volume 2. That's what's happening. Okay? So there's Boyle's. Then you have Charles. Now, Charles looked at it a little bit differently. He said, let us keep the pressure the same. So we'll have volume 1 over temperature 1 is equal to volume 2 over temperature 2. Yeah, so that was what Charles said. We also had Gay-Lussac's law. And what Gay-Lussac was saying, all right, keep the volume the same, so pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Okay, keep the volume absolutely the same. So these are the three situations you have, but in each case, for Boyle, we kept the temperature constant. For Charles, we kept the pressure the same. And in Gay-Lussac's, we kept the volume the same. So those are our resulting formulas that we have. Now, there is also the ideal gas law. Now, the ideal gas law is different, okay? It is different in that, ladies and gentlemen, you don't have a before and an after. You have a what's happening right now, the selfie, if you will. It's just like having the gas, click, there it is. There's your ideal gas law. And the ideal gas law for that, guys, happens to be PV equals nRT. So what are the parts? Well, we have pressure. We have pressure. We have volume. Here it's the number of moles of gas. R is the universal constant. And then last but not least, good old T, well, that is kind of a no-brainer there. That's the temperature. So those are the parts. And again, you're not solving any problems on this one as of 2017, okay? But that's what it looks like, okay? So with that, moving on here, let me see. We also talked about the idea of STP. STP. Standard temperature pressure. With standard temperature pressure, we have 0 degrees Celsius is our standard temperature. That is also equal to 273 Kelvin. The way that we convert from Celsius to Kelvin is adding 273. If we go backwards, taking it from Kelvin to Celsius, we subtract 273. The pressure, the standard pressure is 1 atmosphere. Okay, that is STP. This is what you would get at the beach, okay, which is going to be the last part because all the gas problems I have worked out in the separate videos. You can check those out. This is just a concept only, big picture overview of the chapter itself. So with that, we're going to do one last thing. We have the air pressure equivalence at the beach, or otherwise known as Vamos a la playa, oh, 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 vamos a la playa. Okay, so at the beach, we know that we have 1 atmosphere, which is equal to 760 millimeters of mercury, which is equal to 760 torr, named after Torricelli, the guy who invented the barometer. Okay, now that also happens to be equal to 30.16 pounds per square inch. We have that also, which is also equal to 101.3 Kepa. Okay, so we also have that as well. So all those, ladies and gentlemen, happen to be the exact same air pressure, that being at the beach, but notice they are the different units. So there's a way of converting that. Okay, and again, you can check that out in another video. So that's basically it. Looking at the thing here. So we started talking about the idea of the gas chapter. We said that gas, well, it's made of particles, which are made up of molecules and atoms. Gas deals with pressure, which is force over area. Now, how is it that gas creates pressure? Particles hitting the sides of the container, what it may be. It may be a balloon. It may be a gas tank. It could be a number of things, but it's a container. So with that, you get pressure, which you have a connection with temperature and volume. So all things being equal, if the temperature goes up, pressure goes up. Temperature goes down, so does the pressure. Why? Well, if the temperature goes up, there's more kinetic energy of kinetic particles. Okay, if we look at volume, if the volume goes up, the pressure goes down because there's a lot more space for the particles to run around in. If you drop the volume, in other words, make the volume a little bit smaller, but you kept everything the same, the pressure is going to go up. And then we talked about the different gas laws, basically using pressure, temperature, and volume. We looked at Boyle, Charles, Gay-Lussac's, and the ideal gas law here. And then, of course, we have STP, standard temperature pressure, which is 0 Celsius, 273 K, 1 atmosphere, and 1 atmosphere at the beach, okay, is that. Oh, one last thing, if they don't catch it. The number of moles of gas in an ideal standard temperature pressure thing is 22.4 liters. All right. Hey, this is the overview for Chapter 10. I hope people will take advantage of it. And goodbye, good luck, and, you know, Jesus loves you.